Hello and welcome to Lecture 67 of my class from Data to Decisions. I'm Chris Mack, your professor, and in this lecture we'll continue our series of lectures on the topic of design of experiments, and we'll talk about a very important concept in the design of experiments called blocking. We briefly mentioned blocking in a previous lecture. Let's go through that again very quickly. Suppose I'm applying a certain treatment, that's the kind of language we use in the design of experiments, to a result, and I have two options, treatment 1 or treatment 2. So if we're thinking about a classical science experiment, these would be two different values of the predictor variable. And then I get two different responses. I'll call them X and Y. Here, it would be the response from treatment 1, response from treatment 2. And what we want to know is the difference in the results. Often, that's the only thing that really matters if we're trying to, say, optimize a process, find the treatment that provides the best results, things like that. The difference in the results is what's important. Of course, not in every case, but in some cases, that's what we want. If you're thinking about a straight line model, for example, then that's equivalent to saying the only thing that matters to you is the slope. The intercept is not nearly as important. So if we want to know the difference between these two measurements, X and Y, well, we want to know them precisely. Therefore, we want the variance of that difference to be small. What is the variance of X minus Y? We can use the mathematics of how to compute a variance and show that it's the variance of X plus the variance of Y minus 2 times the covariance of X and Y. If X and Y are completely independent of each other, the covariance is 0, then we see that the variance of the difference is twice the variance of each individual item, assuming that they're identical. It's the sum of the variances of X and Y. But the covariance term is subtracted off because of this minus sign. That gives us an opportunity to lower the variance difference. If we can increase the covariance of X and Y, we can lower the variance of X minus Y. That's a fancy mathematical way of saying if I add the same error to both X and Y, that same error will cancel out when I subtract them. That's all this means. And if I can construct my experiment so that the measurement of X and Y happen in a way that whatever random errors that occur are likely to affect both of them the same, that's the same thing as increasing the covariance between those measurements, and we will lower the variance of the difference. We use a technique called blocking to achieve this. Blocking is related to another topic called covariant analysis. So let's take a look at both of these now. We often have uncontrolled inputs into our process, some of which we can measure. We can know what those variations are, but we don't have the option of controlling them or eliminating the differences. And we can use either blocking or covariate analysis, and sometimes both, to remove that effect we're not interested in, what we call a nuisance variable. Nuisance variable might be different measurement tools, different process batches, spatial variations, temporal variations. They're all things that are real, they're happening in our process, but they're not what we're interested in measuring. But they're affecting our results, and they will add noise to the real effect that we're trying to understand unless we can somehow lower that noise. Blocking does this by grouping the experimental results that you wish to compare into blocks that are similar to one another. So when I want to compare two results, let me make those two results on the same measurement tool. When I want to compare two results, let me put those specific two results in the same process batch, or put them close together in time, or in the same space of my spatially varying experiment, for example. That's blocking. Covariate analysis, on the other hand, takes my uncontrolled and measured input and sticks it in the model. We put it in the model, we model the effect of that uncontrolled nuisance variable, and then when we're done, we simply throw it away. We don't care about that nuisance effect, but we use it in the model to get a more accurate result from our model. Let me show you how that works. Suppose I'm testing process inputs and then I'm measuring the response. And when it goes through the system, it might go to tool A or it might go to tool B. Because of the nature of my manufacturing process, I can't select between the two. It just sometimes go to A and sometimes goes to B, but I can't observe it. That is, I record which tool that measurement went through or that process went through. Now, I add an indicator variable in the model for tool A versus tool B. I know which tool it went through, even though I'm not controlling it, and I suspect there might be some bias, some difference in the result if it went through A versus B. So I add an indicator variable that says 1 if it's A and 0 if it's B, let's say. Put it in the model. What that does is allow me to look for an offset. So just a simple fixed offset between the two tools. If I put it in the model and that coefficient of the term is not significant, then I realize that the difference is not important and I can drop that term from the model and ignore it. But if that coefficient is significant in whatever way you want to define it, sometimes it might be even marginal, even a little bit significant, might be good enough for keeping it for these purposes. If that coefficient is significant so that you can actually measure the tool bias, then you keep it in the regression. But here's the key. It's a nuisance variable. I don't really care. I keep it in the regression in order to get a better estimate of the coefficients of the model parts, model variables I do care about. So when I'm done fitting, I simply throw that term out of the model when I'm going to use the model for whatever purpose I'm. So the whole idea is to get a more accurate estimate of the variables I do care about by including the nuisance variable in my model. That's called covariate analysis. Blocking can use covariate analysis, but it designs the experiment to minimize whatever those biases might be. Let me give you a very classic example that's kind of fun. I've invented a new sole, the shoe, and I think it's going to last a lot longer than the old sole. But we want to test it. We want to test it in real life situations. So we've gathered 100 volunteers to test new versus old soles. So they're going to go out and they're going to wear these shoes for 6 months. And at the end of that 6-month period, we're going to measure new soles and the old soles and see if there's more or less wear in the new soles versus the old soles. What experimental design should I use? Well, kind of the way many people would think about it would be randomization. I take that 100 volunteers and I randomly assign half of them to wear the new soles and half to wear the old soles, and I measure mean wear of each of them when I'm done. Well, we need randomization because people are different. Some people walk on concrete all the time for lots of miles, and other people walk on carpet for only a small amount of time. And some people kind of drag their feet, shuffle when they walk, and other people are really fast walkers, and et cetera, et cetera, et cetera. Right? Big differences between people. But I don't care about the differences between people. I want to know about the differences between the soles of the shoes. So I consider the difference between one person and another person a nuisance variable. And that's where blocking will occur. Remember, in blocking, we want the two things we want to compare blocked to be the same in the same condition of the nuisance variable. The nuisance variable is a person. So in blocking, I would take every participant and give them one shoe with the old sole and one shoe with the new. Randomly assigned to left or right, make sure that no bias between them. Then I look at the difference each individual person. when I do that, the differences between one person and another person no longer matter very much. Instead, I get to see solely, sorry the pun, the difference between one soul and the other. This is what blocking can do. And I'll bet you can guess that in that blocking experiment, the uncertainty in our measured difference between the two souls will be much smaller than the randomization assignment. So, rule of thumb that many people use, block what you can, randomize what you cannot. So let's talk about some designs that use blocking. The first and most important, randomized complete block design. In the randomized complete block design, we first identify our blocks, process tool A versus process tool B. Then we run the complete experiment in each block. Within each block, the testing order is completely randomized, but the entire block sees the entire experiment. And I replicate the experiment completely in the other block. Examples of blocks or nuisance variables are things like a batch of raw materials, people. One operator might behave a little differently than another operator in some cases. Process tools, measurement tools, time. Right? So if you have some drift in time, you might want to run a complete experiment in as short a time as possible and then repeat this experiment on a different day and in as short a time as possible to try to keep that time drift minimized. These are all examples of blocks. Sometimes it's not possible to run the complete experiment in each block. When that's the case, something called an incomplete block design, and then we try to balance it out with pairs of occurring equally likely in each block. I'm not going to go into balanced incomplete block designs. If you ever find yourself in that situation, you can look up the literature on that topic. Then we're going to model. And modeling looks a lot like covariate analysis in that I'm going to stick a blocking variable into the model here. So beta, or maybe I shouldn't use beta because we've used that variable for coefficients of our model, but B, let's call it. B sub j will be the blocking effect. Different batches of raw materials, different operators, different process tools, etc. And we'll put it in like a covariate analysis. The difference is because we're doing randomized complete block designs, it helps to separate the blocking effect, the nuisance variable, from the variables that we're interested in. And we get a better statistical assessment of what this blocking factor might be. Another interesting blocking design is the Latin square. If we have many nuisance variables, it can be very difficult to do complete randomized blocks. If I have two nuisance variables, then I have multiple combinations of those, and I would have to repeat the complete experiment 4 times, for example. Maybe I don't want to do that. That would only be if 2 levels of the 2 nuisance variable. I'd have to repeat the blocking complete experiment 4 times. Sometimes you might have more than 2 levels of each nuisance variable as well. So it can be sometimes impossible to do a complete randomized complete block design. So we do the Latin square design instead. Explain what that is. If we have 3 nuisance variables, we do something called a Greco-Latin square. Have 4 nuisance factors, hyper Greco-Latin square. I'm not going to talk about those. You'll get the idea of how it works from the Latin square design. An important limitation of this design, it has some valuable properties, but there's an important limitation. The number of levels of each blocking variable must equal the number of levels of the primary variable. So if I'm varying my predictor variable in my model and I give it 8 levels, then I have to have 8 levels for each of the blocking variable in order to use the Latin square design. So obviously, not every experiment will this be an appropriate design to use, but some of it will. Also, another restriction, the Latin square model assumes that there are no interactions between the variables, in particular between the nuisance variables. So let me give you an example, and this will make it, I think, a lot clearer. Suppose I wanted to test the effect of a gasoline additive on the amount of emissions. Right? To do that, I have to put the additive in a car and drive it around. Maybe I have to drive it around for a while, right? For days. Well, I want to try different levels, a little bit more, a little bit less, and I want to repeat the experiments multiple times in order to get good statistics, right? Well, that can take a long time, because now let's suppose it takes me 2 days to properly test one level of additive. I want to do 4 levels of additives. I want to do 16 combinations, so I want to repeat each experiment 4 times, let's say, right? You might imagine it take over a month to do these tests. So for convenience, I decide to have 4 cars and 4 drivers. And that way I can get things done a lot faster, 4 times faster. But that leads to nuisance variables. That is, I don't care about the difference between car 1 and car 2. I don't care about the difference between driver 1 and driver 2, even though I suspect that different cars and different drivers will impact the effect of this gasoline additive on the emissions. So I want to block those nuisance variables, and I can do that with the Latin square design. The Latin square design looks something like this. Driver 1, car 1 would see some treatment 1, so the level of the amount of additive here. Car 2 and driver 1 would see treatment level 2, level 3, and level 4, etc. And then each driver would have a combination of different drivers in different cars. So on one day, driver 1 is in car 1, driver 2 is in car 2, and driver 3 is in car 3, driver 4 is in car 4. And then another day, they switch around until all the combinations of cars and drivers are met. So I've got 16 combinations. I've got 4 treatment levels that I repeat 4 times, so I have 16 experiments. But if I organize them in this way, I can block the driver and the car. I do that in this 4x4 Latin square design by making sure that each treatment occurs only once in each row and only once in each column. And every combination is covered. That's why we have to have the same number of levels for the nuisance variables and the treatment, or the factor I care about. Also, we're going to randomize this design. So we'll usually ask our computer, although there are tables of Latin square designs, and you randomly pick the version and order in which all of this stuff happens. So it's fully randomized, even though it looks very regular here. You see what I did to create this: T1, T2, T3, and T4. And then the next row down, I shifted it off to the 1 and wrapped the T1 around to the other side. And I keep that to achieve the goal of each treatment occurring only once in each row and once in each column. Now, this is not a complete block, because every combination, cars and drivers and treatments, are not being applied. But it has a specific type of balance, provides very, very important property, that is orthogonality. That is the driver effects and the car effects, the row effect and the column effect, these nuisance variables, are orthogonal to each other and to the treatment, as long as there's no interactions going on. That allows me to model it with 2 nuisance variables, which and not have to worry about any interactions between them because they're orthogonal. Well, that's a very, very brief description of an interesting topic on blocking. There's a lot more to be learned, but well, we're going to move on. So let's look at what we have learned so far in this lecture. As always, you should be able to quickly and easily answer these questions. If not, please go and do the material again. What is blocking? Why would you use blocking rather than using randomization only? What is covariate analysis and when is it used? Explain the randomized complete block design. And finally, explain the Latin square design. Well, that's our lecture on blocking. Next time we're going to cover factorial designs. Till then.